Okay, welcome back everyone to part 2 of week 1's lecture material. We will now talk about pooled OLS in a panel data context. So again, let's jump right into the material. Um, so first of all, we start with panel data models without unobserved effects. So the whole thing that I talked about in the introduction about statistical magic, we skip for the moment. Nevertheless, we will learn about a couple of estimation methods that can also be applied once we include this unobserved heterogeneity. For now, our model is very simple. So typically we have YIT, which is a scalar outcome variable observed for period t for individual I. And we have a vector of observed characteristics. So we say that this is a k-dimensional vector. Beta is, of course, also k-dimensional. And beta is what we try to estimate. UIT is simply the model error for individual I in period t. UIT, by the way, is also scalar. So this is just an element of R. In econometrics, of course, as you know, everything is a random variable. So also the x's are random variables because they are not generated in any experiment. We cannot simply assign certain individuals a level of education of 5 years and the next one gets an education of 20 years. That doesn't happen. Yeah. So individuals choose these variables themselves, and therefore, from our point of view, those are all random variables. Now, also notice that beta here is, for instance, a column vector. So an x prime is therefore a row vector, which is the worldwide convention and is one of the weird things in the Wooldridge panel data book. So he uses a very unusual convention for vectors, namely that xit in his book is a row vector. Now, what's the point of this? This somehow avoids like some prime here and there. However, that's super weird, and that is nowhere done. That's not done anywhere else, and therefore we stick to the worldwide convention of having any vector by default being a column vector. Okay, I mentioned already some stuff in the introduction. So here we talk about panel data models, but actually our treatment resembles more a system of equations. So for instance, each individual I is observed in t different equations. And in panel data, they simply happen to be t different points in time. And they also happen to include exactly the same variables. However, you could also think about a system of equation where for a single individual, you, for instance, have two different equations. One is looking at the salary and the other one is looking at some completely different outcome variable. Yeah. And yeah, you could also treat the models as a system of equation. Because here we do not make any use of the additional information that we have by having the same individual over different periods of time and using the same variables. We do not exploit the power of panel data yet. Okay. Now, also some repetition. Of course, in our framework, we let n go to infinity while t is fixed, because in microeconomics, we have short panels with lots of firms, lots of individuals, but very few time periods available. So therefore, also our sampling assumptions on the individual dimension is most important. And what we assume in this course is that we mostly assume that the individuals are simply random draws from a large population. So this allows us to work with a generic individual I, because they're basically all the same, right? Of course, this assumption can fail, for instance, when you have clustering. So, for instance, you cluster people in the Netherlands and you happen to have people that come from the same family, from the same region, this kind of stuff. And those kind of cannot be treated as truly independent. However, we will ignore this for the moment and simply assume that we have independent draws from a large population. In the linear models that we consider, we will typically not need to make explicit assumptions about the time series dimension. Some assumptions about the time series dimension are going to be implicit in certain rank conditions that we have to impose for consistency, or to be more precise, for identification of estimators. Um, in particular, as we will see, once we include unobserved effects, we cannot allow, for instance, for perfect dependence across time. So for instance, that every variable in each time period is simply the same. That will not work if we include individual heterogeneity. Moreover, in nonlinear models, sometimes we do not only let n go to infinity, but also t. Okay, back to our panel data models, and let's start with the usual least squares estimator. Again, like for the notation here, when we write this x prime beta, what we assume is that the first component of x is actually the constant regressor. So you see that constant component is simply 1. So we implicitly, by this notation, include an intercept in the model. Okay, now again, we completely ignore that we have a panel. We simply treat it as if we have more data. So the classic approach is that we simply try to find the beta that minimizes the sum of squared residuals, right? That is like what we always do in your introductory econometrics course. So what we're trying to minimize is the residual here squared over the whole sample. Okay, so now, of course, if we do that, we can simply find the beta that satisfies this condition by using the first order condition, meaning by simply taking the derivative, which has to be 0, evaluated at the optimal beta hat POLS here. So, of course, that's very simple now. We take the whole thing here to the other side. So xit times xit prime times beta hat OLS comes on the other side. And therefore, this will be the final form of our pooled least squares estimator. So this is pretty much the same thing as you have seen in any other course before, most likely. Just that we have a double sum here, and maybe in time series you miss this sum, and maybe in a previous econometrics course you miss this sum when you look at the single cross section. Okay, so now what happens if our n goes to infinity? So this is hopefully for many of you a little bit of repetition. Since we assume IID draws, we can apply a weak law of large numbers. So we just take the prelim, and these sample averages converge to population averages, right? So you see that the sample averages is simply like replaced by expectations. Now, what do we do in the second step? Well, we simply replace yit by the model. So yit is equal to xit prime beta plus uit. And again, opening these brackets, we see that this part here cancels out with this part here, so that only beta is left. And so the PLEM of our OLS estimator is the true beta plus something. Okay, now what do we need in order to make this something disappear? Well, first of all, notice that we already implicitly used this full rank condition, right? So you see that we have here the inverse of the expectation of xit prime, the sum over the time dimension. And we have the inverse, so we need to assume that this inverse actually exists. So this is the full rank condition. And this is clearly violated if some of the x's are linearly dependent. So for instance, if your x2 is the same as 2 times x3, then the dimension of this matrix will be less than k and therefore not invertible. The next thing that we need is orthogonality of the model error and the observed characteristics. Orthogonality simply means that these things are uncorrelated, right? So because the model error always has mean 0 when we have an intercept in the model, uncorrelatedness is the same as saying that the expectation of the product of x and u is 0 for every t, right? Um, this condition here is sometimes also called contemporaneous uncorrelatedness. So this is the term that we will use. Yeah, so because it's kind of x is uncorrelated to u in the same time period. Some people and books also call this condition predeterminedness. However, in our course, we will reserve this term predeterminedness for something completely different. Yeah, so this is the term that we use. This is sometimes seen, and it's a little bit confusing, unfortunately. However, this term will mean something completely different in this course. Okay, what's next? Now, this condition here, this contemporaneous uncorrelatedness, is also called a moment condition, right? So why is it called a moment condition? Well, if x is a random variable, then the expectation of x to the power k is called the kth moment. Yeah? So in here we kind of have like the first moment of the product of x and u. Now, what we assumed was actually too strong, right? So we assumed that this thing here is 0 for every t, but what we actually need is that this thing is 0, which is of course an implication if all these terms are 0 for every t, right? So in principle, we can make the assumption a little bit weaker in order to get a consistent estimator. Namely, we can pool the moment conditions. Yeah, so pooling will mean that we simply sum over all moment conditions here. Yeah. Now, why do we not simply assume this condition? Well, I mean, it's actually simply difficult to come up with a situation where this contemporaneous uncorrelatedness does not hold, while the pooled moment condition does hold. Yeah? Because then it would mean there is some canceling across the time periods, which is often unreasonable. So normally we would stick to the contemporaneous uncorrelatedness assumption. Now, something important. What we used so far is really we have the data on the IT level. However, we can make our OLS estimator more similar to what we already know by stacking up the data. Yeah? So this is also kind of where this idea of a system of equation comes into play. Now, for instance, we can simply stack the yits, so yi1 to yi capital T in one single vector, which we call yi. The xits, they are kind of put into a single matrix. Yeah? So you see that because we put a prime on all the xits, this is a t times k matrix, so that here there is no prime. Yeah? Beta is still in r to the power k. And also the u is stacked. Okay, so we can write the model like this, and this looks pretty much like a simple cross-sectional model. Yeah. Okay, now in this matrix notation, this is something very useful to remember. Like these cross product of these matrices will really correspond to the sum over t. Yeah, so these kind of things here you should remember. Also, the cross product with this matrix with this t-dimensional vector will again be simply the sum. So you see that here kind of the dimension of this object here is k. The dimension of this here is k times k, because this is like a k vector, this is a k row vector. The result will be a k times k matrix. Okay, so this is a little bit of notation, which is very useful. So this type of notation with only the I index, we will use many times in this course. However, we can make this even more compact by stacking the stacked vectors and stacking the matrices. Yeah, so now we can really write the full data set like this. Yeah? Where this is now, the X is now an NT times K matrix, and the U is an NT vector. Yeah? So this contains all the data. And this looks, of course, very familiar if you have taken any econometrics course before. Therefore, we can write the pooled OLS estimator in 3 alternative ways. So this is the most compact form. However, my personal favorites are number 2 and number 3. Why that? Well, number 2 actually shows you like where the law of large numbers is applied, right? So here you have the average across I, and that makes very clear that if we let n go to infinity, here some convergence is happening and here some convergence is happening. And also what we will use is this form, which makes very clear that we are in a panel data set. Yeah, so with this additional sum over t. Okay, so I think that was pooled OLS in terms of consistency. Now, for consistency, we only used like this contemporaneous uncorrelatedness, meaning that each xit is orthogonal or uncorrelated with the model error uit. And we have used the full rank condition. Yeah, so this thing has rank k. This was enough for consistency. So now, what else are we interested in? Well, we want to do inference, we want to do testing, and for that we need an asymptotic distribution. So let's scale the OLS estimator by square root n and subtract the true value. That is easily shown to be this thing here. Yeah, so that is most easily seen. Okay, where are we? Pretty much here. So you subtract beta and you multiply this by square root n. Yeah, so that's what you get. Okay, where are we? Here. Okay, so now what happens as n goes to infinity? So we already talked about it, that this thing here, like in the inside, this will converge to the expectation by the weak law of large numbers. And because this thing has full rank and the inverse therefore exists, and because also the inverse is a continuous function except at 0, yeah? By the continuous mapping theorem, the whole thing, including the inverse, will converge to the inverse of the expectation. Okay, now next we apply, so this is like the first term, we have dealt with this term, and next we deal with this term, and for that we need the central limit theorem. And well, under our sampling assumptions, it's easy to show that this term here converges in distribution to a normal distribution with this mean here and this variance. Yeah, so simply this thing here times its transpose in expectation. That's the variance. Now, of course, we have assumed contemporaneous uncorrelatedness. That means that this expectation here is this 0. And simply by opening this bracket, we get this asymptotic variance. Now, we have one thing that converges in distribution, and we have another thing that converges in probability. So how do we combine these things? Well, we have Slutsky's theorem. If we have two sequences of random variables, and one of them converges in probability to a constant, and the other one converges in distribution to some random variable, then the combination of these variables converges in distribution to this distribution times the constant. So that means that the weaker form of convergence survives. And therefore, by Slutsky's theorem, we can combine these things. And we see that the asymptotic distribution of the pooled OLS estimator will be normal with mean 0. And now we have this variance that may look complicated, like a sandwich form variance, right? Okay. Yeah, so again, the variance V has, as I said before, the sandwich form. So where this thing here can be regarded as the bread on both sides, and this part here is the filling. And maybe you have seen a simpler form of this, which can be obtained by additionally assuming homoscedasticity, which means that the variance of the model error, which can also be, of course, written as the expectation of u times u prime, is independent of x. Yeah, so you see that there is no x on the right-hand side. Yeah, so this is simply some sigma squared, some positive number, times the identity matrix with dimension t. Okay, so of course, if on the right-hand side there is no x, that means the conditional expectation coincides with the unconditional expectation. And if you use homoscedasticity, you can write this term here as a combination of two expectations, where the inside expectation here is conditioning on x, and the outside expectation is with respect to the marginal distribution of x. Yeah? So this is kind of the law of iterated expectations. Now, in the inside expectation here, when you condition on x, that means x will act as if it was a constant. And therefore, you can take it out of this conditional expectation. And now you are left with this thing on the inside. Now for this, we have an assumption, namely homoscedasticity. Therefore, we can replace this by sigma times the identity matrix. And yeah, all we need to write here is therefore the sigma squared times whatever is left, this x and this x. Yeah. And now in the next step, we will take this expression and plug it in here. And we will see that there is a simplification, because this thing here cancels with one of the inverses here. Yeah? So this is precisely what is written here. The asymptotic variance therefore simplifies substantially under homoscedasticity. Okay, now how would we estimate this asymptotic variance under homoscedasticity? Well, we first need an estimator of sigma squared, which is an estimator of the variance of u. For that, we can define the residual ui hat, which is the observed xi minus the observed yi minus the observed xi times the estimated beta. And well, if beta hat is consistent, well, so should be the u hats. Yeah? So these u hats will be good estimates, will be close to the actual ui's. And well, then we can define an estimator of sigma hat in the following way. And therefore, we get an immediately a consistent estimator of the variance matrix V by replacing, for instance, this expectation here is replaced by the sample analog, so the population mean is replaced by the sample mean, and we have an estimator of sigma hat squared. And again, because this is a continuous combination of two consistent estimators, the whole thing will be consistent by the continuous mapping theorem. Okay, now what is the issue with homoscedasticity? Well, often it is not realistic. So because it assumes that the spread in the error term does not depend on the level of the explanatory variables. So this can be unrealistic when you think of a wage regression. So you have education as one of the observed x variables. Then you will see that for low levels of education, there will not be so much spread in the wages. And for higher levels of education, there are some people that have a high level of education that turn out to be CEOs of Google, and some other people go into academia, and therefore there is quite a large spread in between these people. Okay, now what do we do when we have the suspicion that there is heteroscedasticity? So no homoscedasticity, but rather the opposite, heteroscedasticity, namely that the variance of u depends on the level of x. In that sense, we simply, okay, so 1 second, it stopped sharing for some reason. When that happens, we go back to our sandwich form here, and we replace all the population means by sample means. So we will maintain this sandwich form of the estimator. And this we had here, this is robust to heteroscedasticity, as has been shown in a really super influential paper by Halbert White in 1980. Yeah, so this paper is extremely influential. It's like number 9 of the list of the most cited article in economics, according to this website here. You can check it out if you're interested. Nowadays, it's not only called White estimator because, well, there's other people that have discovered the same thing, but or something similar, but it has not been recognized beforehand. So Halbert White independently rediscovered some of the theory and also extended it in some way. So nowadays it's called the Eicher-Huber-White standard errors. Now, what we will see is that other econometrics papers make it quite high on this list of the most cited articles, and some of which we will also discuss here in this course. So for instance, GMM, which is this paper of Lars Peter Hansen, who also got the Nobel Prize for this. And we have another super famous paper by Ariano and Bond, when we look at dynamic linear models with unobserved heterogeneity. Okay, final words about exogeneity in panel data. Now, again, what we've seen for the pooled OLS estimator is that we need pretty weak conditions for consistency. For instance, we only need pooled contemporaneous uncorrelatedness. Yeah, so this thing is enough in order to show consistency, of course, assuming that the rank condition is met. Yeah. However, if you want this thing, the OLS estimator, to have a causal interpretation, you should think about whether also contemporaneous exogeneity is reasonable in your particular application. So in panel data, that means that it's not just that UIT and XIT are uncorrelated, but rather that UIT is uncorrelated with every measurable function of X. Yeah? And this has to hold for every time period and every individual. So it is in principle possible that there is an X square hidden in the error term. And when you do pooled OLS, you get a consistent estimator because X squared can be uncorrelated with X. Yeah. However, of course, the effect of an increase in X will not only depend on the beta that you measure with pooled OLS, but will also depend on the X square that is hidden in the error term. And therefore, uncorrelatedness is often not enough for having a causal interpretation. Yeah. If you can assume contemporaneous exogeneity, this rule out these weird cases. Okay, next, yeah, so of course, like contemporaneous exogeneity is clearly implying contemporaneous uncorrelatedness. Again, by using the law of iterated expectations, you can easily show this. This big expectation with respect to the joint data is split into one expectation that is conditioning on X, and the outside expectation is with respect to the marginal distribution of X. On the inside expectation, because we condition on X, this thing here acts as if it was a constant, comes out of the expectation, and this part here is now 0 by contemporaneous exogeneity. If we have contemporaneous exogeneity, we call XIT exogenous, and we call XIT endogenous if XIT is potentially correlated with the model error. Yeah, so you see that it's not precisely logical opposites, but endogenous in the literature everywhere means that you also have inconsistency of the pooled OLS estimator, and therefore we say endogenous if this condition is true. Now, this is again looking ahead. Once we really start exploiting the power of panel data, mainly by including unobserved individual heterogeneity, say account for individual ability, motivation, this kind of thing, we will again see that contemporaneous exogeneity is not enough. A condition that you will often see in textbooks is this here, strict exogeneity. In the panel context, that means that U in period T is exogenous, is mean independent of the axis in the whole time period, in all time periods. Yeah, you see that it's not only xit here, but it's xi1 up to xi capital T. Now, this condition is of course stronger than contemporaneous exogeneity because this condition here does not, for instance, allow for feedback. Yeah, so that means the model error is uncorrelated with past, current, and future regressors. What is an example of feedback? Feedback is the case when you look at production is, for instance, one of your input variables, one of the x's. Sorry. Production is the y, and a shock to production is represented by the model error. Yeah? So for instance, there's a macroeconomic shock that hits the production level y. And if this shock has any correlation, any influence on future capital and labor inputs, which are represented by future x variables, then we have an example of feedback and strict exogeneity fails. Yeah, so when you make this assumption with strict exogeneity, you have to think, is feedback important for your model? Okay, so to summarize, we have looked at the pooled OLS estimator in a panel model, but we have not exploited any powers of panel data models. No, we could have equally regarded the T time periods in which we observe individual I as T separate equations which have nothing to do with each other. In our case, well, they happen to have the same variables, but well, the theory would also work if they were completely different variables. No? And well, we have also seen that the mechanics of pooled OLS is pretty much the same thing of the regular OLS that you already know. And that can, for instance, be shown by simply stacking the data. For consistency, we only need pretty weak conditions. So for instance, we need the pooled contemporaneous uncorrelatedness, and we need the full rank condition. Our assumptions on the variance don't play any role for consistency. However, like the expression or our estimator of the variance depends very much on our assumption on the conditional variance, because homoscedasticity, very simple form, heteroscedasticity, more complicated sandwich form. And under mild conditions on the moments of x, we also can show that the OLS estimator is asymptotically normal. And as I just said, if you have homoscedasticity on top, you have a very simple form of the asymptotic variance, but homoscedasticity is often unrealistic, so it's often better in applications to use the heteroscedasticity robust estimator of Eicher-Huber-White. By the way, using the robust estimator does not always come at a cost. So these robust standard errors, they tend to be larger in applications, but it's not always the case. They can also be smaller than the regular OLS estimators under homoscedasticity. Now, OLS can be consistent and still not have a causal interpretation. Yeah? We can only have a causal interpretation if we are willing to impose stronger conditions, for instance, strict exogeneity. Okay, so that's it for this video. If you have any questions, let me know. Okay, see you in the next one.